Hello class, this is our last asynchronous lecture, and we'll be discussing the latter half of sexual selection that we started on Friday. Whereas before we talked about male-male competition, which is half of sexual selection, we're going to talk about female mate choice, or more accurately, the way to describe it is the choice of the sex that invests the most in reproduction. That's typically the female sex. So let's get started. So this is what has become quite a famous behavioral study in sexual selection in long-tailed widow birds. And so these blackbirds, the males have an extremely long tail, as you can see. Anderson, 1982, this seminal paper. And what Anderson did, there you go, that's what he looks like, was that he took a look at the reproductive success of these males, specifically by their tail length. And so he measured reproductive success by the mean of nests per male, so how many nests his genes were represented in. And then he manipulated tail length. He cut short the tails on some, and he artificially extended the tails on others by gluing the tails using super glue. And so what did he find? Well, those individuals that he cut the tails on were able to put their genes in much fewer nests. But those individuals that he artificially extended the tails on were much more successful. So females exhibited a clear choice. And so it's this idea that through sexual selection, females are driving because they control the selection pressure for what phenotype, what genes for what phenotype get carried into the next generation. You can imagine that if this long tail actually had a genotype associated with it rather than just super glued, these genes are going to be more overly represented compared to the short-tailed genes in the next generation. And therefore you should expect for long tails to become more and more common. So because of their disproportionate investment in gametes and parental care, females are almost always the choosy sex. And there's two different ways to think about the benefits that females can get by being choosy. Direct benefits, and these are things that directly affect the female's fitness. Either her own health, or through reducing the amount of parental care that she needs to invest. And then there are indirect benefits, and those are essentially benefits not directly to the offspring, but indirectly to her fitness by directly benefiting her offspring. So let's take a look at specific examples. First, direct benefits. And so one clear one are nuptial gifts, which we've talked about before. And this also includes sexual cannibalism, the ultimate nuptial gift. So by choosing specific males that offer better nuptial gifts, even if that nuptial gift is themselves, is a direct benefit to the female's own fitness. It is a literal food source. And here's some good behavioral study system. Madian Andrade studies spiders, including this one, the redback spider, also known as the Australian black widow. And she found that female's body condition, so positive numbers are good body condition, negative numbers here are poor body condition. And it shows the number of mates they have. So they're more likely to have more mates if they're in poor body condition. And the solid black rectangles indicate which mates the female consumed. So you can see there's a pretty stark difference between poor body condition females will engage in sexual cannibalism as opposed to those that have good body condition. So hungry females cannibalize males. So this is evidence of, we can infer from this that there is a direct benefit from cannibalizing these males, because those that don't need it don't do it. Another form of direct benefit is in parental care. So it may be advantageous for a female to choose a mate who is going to be a good father to her young. And the direct part of that is basically relieving her burden. So let's take a look for evidence that we see in that, for that. Courtship feeding, for example. So this is often... There's going to be no place for me to put my face, is there? Oh, no, we're good. Parental abilities are frequently displayed in courtship situations. So often you see this where males, as part of the courtship ritual, will bring food, right? So this is very similar to a nuptial gift, though it more closely mirrors the behavior that the male displays to the offspring. Right? So he's literally feeding the female in the same way that he would feed young. Right? And we see this throughout the animal kingdom, including humans, which sort of, to my, in my opinion, is sort of one of the strangest kind of like Western cultural marriage traditions, sort of feeding each other a cake. I don't know why I'm kind of weirded out about it, but it just seems so strange to me. But perhaps it exists because there's a sort of an underlying evolutionary history with courtship feeding. That seems like a bit of a stretch, but funny to think about. Repertoire size. So in many different species, and when I say repertoire size, this is usually in bird species, there's usually a tight correlation between repertoire size and the quality of the chicks. And so in species that have biparental care, that is both parents feed, typically if you have a father that has a relatively larger repertoire size, they tend to be to provision more at the nest. And so these end up being proxies for parental care. Another one is carotenoid colors. And so colors that are responsible for reds and yellows and orange. Across taxa, it's usually fish and birds are sort of the classic species, because you do get some just wildly bright reds and oranges among these different taxas and dimorphic species. Right, so, but separating the effects of direct parental investment and indirect genetic quality can be difficult. Right, so in that past graph that I showed you with repertoire size, correlating with larger chicks. How do we know that it's directly due to the behavior of the fathers in parental care, or perhaps just the fathers with the larger repertoire size just had better genes, and that's the connection? And so maybe that's the link here, where brighter males with these richer warm colors. Where does the benefit come from? Is it because those richer warm colors correlate with parental care, or does it correlate with good genes? So how could you test that? How could you design an experiment so regardless of what answer you got, you could say either or? This is just an example of how they measure intensity of the carotenoid colors through the reflectance and wavelength measurements. So if you want to pause and think about this, how would you test? How would you tease apart indirect genetic quality and direct parental investment correlated with some sort of phenotype? So I guess you can pause. I don't have to wait, do I? So you would do, as many people have done before, what's called a cross-fostering experiment. If you want to decouple genetics from behavior, it's pretty simple. Your chicks, you need to get rid of that confound, right? What's confounded? Well, in the measurement that you're doing, which is usually some sort of like quality of the offspring, you can't tease apart because one offspring will have the genes and the effects of the behavior from the same father. So no matter what you get, you don't know what's causing it. But you can tease that apart, right? You can take an offspring that has genes from one father and give it to a different father that it's not related to, and then they'll be affected by that father's behavior. They'll be raised by a different father that they don't share the genes. And then you can take a look and see what matters when you measure some quality of that offspring. Is it because of the genes or because of the behavior? And so let's take a look at this example. So this is graphing the standardized tarsus length of fledglings. Tarsus is the bone right here. So longer tarsus tracks very well with overall body size. And in this species, blue tits, which are European species, the bigger you are at fledgling, the greater chances you have at surviving. And we take a look here at the yellow hue of the foster father. And there's a direct correlation between the intensity of the yellow hue and how large you are as a fledgling. And it's the yellow hue of not the genetic father, which there is no relationship with. It's a big circle of dots. But when you take a look at how bright the father that raised you is, well, then there is a benefit. So it does seem that, at least in some species, that the richness of the color of the fathers correlates with how well they participate in parental care, how effective they are at raising young. Also, these indicators are likely, or these characteristics are likely health indicators. And this can be important. Well, for example, blue-footed boobies, when their body condition decreases, they have less subcutaneous fat, or they suffer from some kind of parasitic infection, the intensity of the blueness on their feet decrease. And and blueness is of their feet is an object of female mate choice. And so there's an obvious direct benefit for females that are to avoid males that are sick, contagious, have parasites, or even the wrong species. It can be a species identifier. So what about indirect benefits? What if females don't get any kind of direct benefit, which is quite common? Nature's filled with deadbeat dads, and they tend to be much more elaborate than males of monogamous species. When we think about those species that have very intense dimorphism, it's usually in species that are not monogamous and in species that do not have biparental care. So there must be something driving it if it's not direct benefits. So in the absence of direct benefits, how do females choose their mates? Why do females prefer particular males in the absence of direct benefits? Right? Shouldn't every system go that way? Why are there species where females do not have direct benefits? Why are there species where there's just maternal care and not biparental care? So the indirect benefits, these are the benefits that benefit the female not directly to herself, but indirectly in her offspring. Remember, she's sharing these offspring. She's obligated to share her offspring with someone else. In order for her to pass her genes off into the next generation, she needs a male to contribute his genes. So does she get any benefit at least for her offspring, which are the carrier of her genes? So let's take a look at the satin bowerbird. So by measuring male traits and female visitations, we know that in the bowerbird, females like more blue decorations. Oh boy. Gotta find my power cord. Bear with me. Okay. Thanks for your patience. We know that in the blue satin bowerbird, or the satin bowerbirds, females like blue decorations. They like bright UV coloration, symmetric bowers, song elaboration, and they also like no interruptions. So let's take a look at this video so you can see exactly what am I talking about. What's a bower?
The rainforests of eastern Australia are the stage for perhaps the sneakiest criminals of the lot. This is the satin bowerbird, a creature with a bad case of kleptomania. It doesn't stop at weaving twigs, he likes home decor too. Blue is his favourite colour. Bottle tops nicked from a nearby campsite are his proudest possessions. He has an eye for detail too, placing them precisely for maximum visual impact. She makes all the right moves, entering the bower to show she's interested. A ring makes the perfect gift. Not impressed? How about a bouquet of flowers? But something's not quite right. penny drops. He's been duped. This isn't a female at all. It's a young male in disguise. And he's here to steal. He's part of a gang of juvenile delinquents roaming the forest, tricking unwary males. In their hideout, they display their ill-gotten gains. It takes up to 7 years for a male bowerbird to reach maturity. In the meantime, they practice making a bower and dancing for each other. But they can never have too many blue trinkets and bling. Time to go out stealing again. And bowers don't come more decadently inviting than this. But this is no ordinary bower. It's occupied by a male spy bowerbird and adorned with an irresistible array of blue treasure and jewel cameras, all perfectly placed to catch the thieves in the act. Like professionals, they approach with caution. Once again, they pretend to be courting females. This time, they work together. One distracts as the other steals the jewels. Spy bowerbird can only observe as they clean out the bower, gem by precious gem. Back home with their stolen goods, they continue to practice their courtship techniques. But Spy Bowerbird isn't off the hook. The male bowerbird who was their first victim needs to replenish his bower. Well, if you can't beat them, you may as well join them.
Get big again. There we go. So, crazy bowerbirds. So we know by studying this species that females prefer all of these things. And this is an example of a species that does not show biparental care. The male donates his sperm, and that's it. He's got nothing to do with the nest or the eggs or raising the young. And we also know that these qualities, more appropriately referred to as signals, because they are proxies for other information that has more of a benefit, or might reflect a good genotype, such as parasite load, blood parasites, body size, and feather growth. So overall plumage color and the UV reflectiveness of the feathers directly correlate with how well the feathers grow, the quality of the feathers, which is obviously good for a number of different reasons. Body size, typically the larger you are, the easier you are, or the easier it is for you to survive in bird species. So interesting things like the quality of the bower and the number of decorations that a male has correlates with how big they are. And body size often has an underlying genotype, genetic cause. It always involves the interaction with the environment. But by a female that picks a male that has a very nice symmetric bower and a whole bunch of blue decorations is, in a way, choosing that their offspring will have genes for larger body size. So this would be an example of an indirect benefit, because these things, these characteristics correlate with things that are important for the survival of offspring. So birds aren't the only one. Here's a nice entertaining video.
Spider silk with the scent of a female. He just needs to follow it. Wherever it leads him. Other males have gone on the same quest and have come to a grisly end. Here's the female, and she doesn't look very amorous. In fact, she kills every male who doesn't match up to her expectations. What can he do to win her over? Dance. Dance for his life. He will need a show-stopping trick to avoid becoming lunch. With his fan unfurled, he begins an ever more complicated series of dance moves to try and seduce her. At last, she succumbs to his advances and allows him to mate with her. He matched her expectations. But she kills him anyway.
So, peacock spiders. And the female choice is based on the male displays in these very charismatic jumping spiders. There's a whole bunch of them. And they're so tiny. So pronged horned sheep. There's great evidence in here for indirect benefits from female mate choice, such as offspring of attractive males survive better. So again, it's a species that doesn't have biparental care, just the female raising. Yet there's a correlation between the attractiveness of your father and how well you survive. And so this is the offspring age on the x-axis and the survival function. So it's essentially, one is that everyone is alive. When you get to 0.5, that means half of the subjects have died. And so we can see as we go along here that attractive males survive more. Ultimately, the life expectancy is the same, but if you have an attractive father, more individuals live for longer, whereas for unattractive offspring of unattractive fathers, there's a die-off very quickly. And those that survive that first die-off will stick around. But that early die-off is largely absent if your father is attractive. And also we see evidence for these indirect benefits because the more attractive you are, 15 being very attractive and 1 being not so much, the females will invest or have to invest more in parental care if the offspring's fathers are less attractive, presumably because their quality, the robustness of the offspring is less. Gray tree frogs is another great example where we see evidence for indirect benefits. Females prefer males with long calls, and eggs fertilized by males that give short calls, well, they develop more slowly. The tadpoles from those eggs develop more slowly. And when it comes to being a tadpole, this is the part of a frog's life where they are the most vulnerable as eggs and tadpoles, because there are just so many more things that will eat you. And then there's something called the Hamilton-Zook hypothesis. So and it states that elaborate sexually selected traits, such as bright plumage, reveal parasite status of males. This allows females to choose parasite-resistant males. And so not only is this good for them directly, but it is perhaps good for their offspring if there is a genetic, an underlying genetic cause to parasite resistance. So the full expression of these male traits is limited by parasite infection. So there have been a number of experiments that show that if you give a male a parasite, those secondary sex characteristics will become less in quality, such as the brightness of your feathers. Females that choose males with exaggerated secondary traits obtain resistance genes for their offspring. Makes sense that you would want the offspring that are carrying your genes into the next generation to be resistant to disease so that they can survive and reproduce. So why not pair your genes with the genes of someone else that can help your offspring live longer? Heritable variation in parasite resistance is maintained due to coevolution between parasite and hosts. And so earlier in the semester we briefly talked about the Red Queen hypothesis, this sort of like cyclical coevolution between parasites and hosts. And so that's the mechanism by which there's always variation that's heritable in your ability to fight off parasitic infections, because diseases or the parasites and the organisms that cause infectious diseases are constantly evolving themselves. And the European starlings. It's a lot of those around right now on campus. European starling females prefer long songs. And we've seen that song signals immunocompetence. There we go. In European starlings. So, individuals that sing longer songs have a more robust immune system, as measured by their antibody response. So, by essentially giving individuals, measuring their average song bout length, which is sort of like so you can come up with a behavioral phenotype or a song singing phenotype. There are individuals that sing shorts, that spend less time singing songs, or when they sing shorter songs, and those that sing longer songs. And you compare that with how well they respond to an infection. So actually capturing these individuals and injecting them with protein from a specific type of protein from a bacteria to see how well their immune responds to it and develops antibodies. And then you compare this and see if there's a trend, and there is. A more robust immune response correlates with song bout length. And so everything that we've talked about here up until now in terms of the indirect benefits of these characteristics are essentially proxies for other genetic-based characteristics that are vital for improving your chances to survive and reproduce. So that's the benefit that it gives to offspring. But there's another hypothesis, and we would call these, what we've previously discussed, the good genes hypothesis. These characteristics are honest signals, honest proxies for underlying good genes. But there's another hypothesis that is just the opposite, and it's called runaway sexual selection, or sexy sons hypothesis. And so it states that the benefit from linked genes for female preference and male traits is what drives the sexual selection. And so essentially, the only reason that these traits, such as collecting blue things and this strange behavior of creating bowers, or having really orange scales if you're a guppy, or having a really long repertoire size. But the only reason that these things have evolved and exist is because they are attractive to the choosy sex, to females in most species. And so let's see if I can't illustrate this and why we call it runaway sexual selection. So in a dimorphic species, there's obviously a female preference for a specific phenotype, male. And their offspring, the females, will have, if there's a genetic basis to this preference and the male phenotype, the display phenotype, whether it be coloration or some kind of behavior or repertoire size, the males will have these characteristics and the females will have a preference for these characteristics. Right? The females will have a preference for these characteristics. Now, as as they cycle through and the females become as the females become mature, and then they start becoming the individuals that are choosing and deciding what male genes are going to get carried off into the next generation. They may have they're going to look for males that satisfy their preference as much as possible. And so if they have a preference for long tails, like we saw in the first example with the widow birds, they're going to choose the male with the longest tail. And so the males that have slightly shorter tails won't get, their genes won't make it into the next generation. And as you go along, as with each subsequent generation, you have this selective pressure for longer and longer tails among males. Presumably, sooner or later, natural selection will kick in, and a long tail will, albeit convey a benefit for female preference, will eventually any cost that a long tail has to your fitness will eventually, presumably, outweigh the benefit of being attractive. We've seen this in a number of species that we suspect via the fossil record have gone extinct, perhaps because of an over-elaboration of sexually selected traits. There is a number of North American ungulates that went extinct before the modern era that had huge antler sizes. Presumably, the only benefit to this would either be through male-male competition or female mate choice, which are two things that are really only important in sexual selection. In natural selection, it was presumed that these elaborate antler sizes made it very difficult for them to forage and physically walk through a forest. So that's an example of where natural selection might catch up and start selecting against these really elaborate traits, and also, if they're linked to preference, selecting against the preference for those traits. And to close out this this lecture, closing out sexual selection in this semester on the biological sex mosaic, I'm going to talk about sex role reversal. And while we've been talking about just females being the choosy sex and males being the ones that are competing for female choice, it's often flipped. Though it's the exception rather than the rule, it does exist. So if males make the larger parental contribution in a species, this is typically what we find, that females are the ones that compete for mates, not males. We see this in jacanas. Females will fight each other to gain access to males. We see that females tend to be more elaborate than males. We see this in Wilson's phalaropes. This is a female on the right and a male on the left. So the females are sort of have the fancier phenotypes. Female long-tailed dancing flies. It's the females that display because they are fighting for male mate choice rather than the other way around. In another great example that I'm sure most of you have heard before, that seahorses and pipefishes have a parental care paradigm, and as a result, it is the females that have to sort of win favor of the males, and they compete for the male mate choice. And if they win, if the male chooses the female, then he allows her to transfer her eggs to a specialized brooding pouch where he fertilizes the eggs and takes complete care and is 100% the only sex that contributes to the parental care 100%. And so to close out the semester, the biological sex mosaic, I thought it was appropriate to show this image of a father seahorse giving live birth to his young, for which he's carried and cared for, and will continue. So it's a good example of how just about anything that you can think of or that is possible, nature has probably already done it. And there are always exceptions to what seems to be the rules, i.e., there really aren't any rules. And that certainly is the case when it comes to biological sex. So, make sure that you watch this video. Well, and this doesn't make sense because if you're hearing me now, you've watched the video. But this material will be covered on the last exam. Okay, thank you, and goodbye.